Hello there and welcome back to this video series on control systems. Past few videos we have been looking at design in frequency domain. We have seen what is a lead compensator and how to design a lead compensator. Then we have seen what is a lag compensator and what are the frequency characteristics of lag compensator and how to design a lag compensator. In this video, we try to combine both of them and see how we design a lag and lead compensator put together. So after completing this video, a student will be able to specify lead lag compensator form and perhaps specify a few properties of the lead lag compensator and design a lead lag compensator. We'll try to see what is the structure of a lead lag compensator's transfer function. The GCS has a form as given by here, in which one is the lead part, another is the lag part, and of course you have a K. Typically, as we have seen, this K is computed using the steady state constant requirement. Okay. Note that in this beta is greater than 1. Transfer function in frequency domain is written as shown here, substituting S is equal to j omega and putting it in time constant form. So you see there is a constant part and there is a dynamic part with k1 is equal to beta k. As is our standard practice, we try to find the value of k1 to satisfy steady state error constant requirement and then find the dynamic part. Part of a lead lag compensator is shown here. You have corner frequencies 1, 2, 3 and 4, and these are defined by values of T1, T2 and beta. Okay. Of particular importance, you see that there is one frequency where the phase angle turns out to be 0. Okay, exactly 0. This occurs at 1 over square root T1, T2. We'll try to use it at an appropriate time. Before we go into the mathematics of it and design using Bode plot, we'll just note that a lead compensator is a high pass filter that can give improved stability margins and lesser settling time, but with a slightly higher gain crossover frequency. On the other hand, lag compensator is a low pass filter and it in general gives increased settling time and lower bandwidth, and this helps in steady state accuracy, and because of this lower bandwidth your high frequency noise is attenuated and you have a pole zero combination near the origin that gives a long tail with small amplitude in transient response. Lag lead compensator clubs the advantages of both lead and lag. Fast response and good static accuracy. Increase in low frequency gain implies good static accuracy, and bandwidth and static accuracy can be increased simultaneously. We'll try to consider this with an example. Let us say you have a transfer function something like this with velocity error constant requirement of 30 second inverse, phase margin greater than or equal to 50, and then bandwidth is 12 radians per second. In width, we see that the requirement of velocity error constant is 30. Velocity error constant is given by limit of s times the gs as s tends to 0, which is required to be 30. So value of k is 30. We'll retain this value of k all through the design so that this kb is equal to 30 is done for us. Thus, the gain compensated plant, there is a T missing here, flat, is GC of S is 30 divided by so and so. We draw body plot of this system as shown in the next slide. This is the body plot of the system, and you see that the gain margin is totally messed up, phase margin is messed up, but bandwidth is okay. But what do we do with bandwidth if the system is inherently unstable? The same we note down here, the system is unstable. Open loop body plot exhibits a bandwidth of 11 radians per second. The closed loop system has a greater bandwidth, but still it is of no use since the system itself is unstable. Just to gain insight and see how we can play around, we'll try to see an arbitrary lead compensator and how it is performing, arbitrary lag compensator, and see how it is performing. We'll do that in the next slide. Try to show that. We'll try to show only the results. I won't show all the calculations that are done. Let us say we consider a lead compensator DC lead, okay, as shown here. I've taken arbitrary numbers just to show as an example, and we saw that this GS GC1 is stable. I've written the system GC1 GS, draw the body plot and find the phase margin, bandwidth, and we saw that this bandwidth comes out to be a bit large. That would imply that the system is sensitive to noise. We don't generally prefer such a thing. On the other hand, if you have a lag compensator as given over here, the closed loop system is stable, phase margin 46 is satisfactory, but bandwidth is very low. So you see here phase margin didn't satisfy here with lead, and bandwidth requirement is not satisfied here with lag. So this has a problem of its own. This has a problem of its own. This kind of indicates we need to go with a lead lag compensator. First, design a lag compensator. We call it part 1, wherein we design a lag compensator, and then we try to see how we go about designing a lead on the top of it. So we choose a new gain crossover frequency where the phase angle is minus 145, and we see that this occurs at 3.52 radians per second as shown in the body plot on the next slide, and we want to choose this as the new gain crossover frequency. This is the body plot of the system with lag compensator we have drawn, and you see that the frequency 3.53 gives a phase of minus 145. These letters are small, but I guess you can zoom it to see. At 3.53, you have a gain of 16 decibels. So if you bring this down, you will achieve the condition that 3.53 is the gain crossover frequency. And we note that to make 3.52 radians per second as the gain crossover frequency, the compensator must provide minus 16 decibels at 3.52 radians per second. So this gives the value of beta to be approximately 7. Note here we need to write 20 log 1 over beta as minus 16, but 1 over beta and minus we can cancel out to say 20 log beta is 16 and beta as 7. We choose a T1 is equal to 1 and write the compensator dynamic part 1 plus j omega by 1 plus j sine omega, and your closed loop, your open loop system transfer function with lag compensator is given here. Plot of the system with lag compensator, that is in part 1, is shown over here, and you see that the bandwidth is around 4.3 radians per second. This is the gain margin, this is the phase margin. We still didn't achieve the required phase margin. We wanted somewhere around 40 and you have 22.5. We now try to design a lead compensator that gives the required phase lead. So, knowing beta, we write alpha. Alpha is 1 over 7. So, the phase lead that it can give is 48.6. And we find omega m to give an attenuation of minus 8.45 as 6.15 from the body plot, and from which we compute what is T2. Thus, we have the lead compensator part as shown over here, and then the open loop transfer function with both the lead and lag compensator included is like this. This is the lag part, this is the lead part. Now when we draw a body plot and see, we came very close to our specifications. We were able to design the lag part and the lead part of the compensator separately. To reach and exceed the specifications, we need to play around a little bit around the values of alpha and beta. We may even consider changing T1 and T2. That part we are leaving here, and this shows one iteration of the design. We'll see the body plot here. The body plot shows that the bandwidth requirement is more or less met, very close. Gain margin is close. Phase margin is close. So we consider the design to be complete at this stage. We saw that the lag lead compensation is done in two steps. First, a lag compensator design, then a lead compensator design. We have shown only one iteration, but the complete process may take quite a few iterations. We may choose alpha independently of beta, and then try that. All these iterations require drawing body plot many times, and thus intensive use of MATLAB cannot be avoided. That is all we have for now. Have a great day.